Good. And let me share a screen. Good. So the people on the Zoom, do you hear me well?
Yeah, we can.
Good. Okay, so let me just bring this one here. Good. So we talk about NP-hardness, and there are two problems that we were talking about. Actually, one was three-sat or satisfiability that we already talked a little bit about it, but we talk more in this session. And two partition and more generally three partition. These are the important problems that you can use for hardness problem. There are other problems like Hamiltonian cycle, Hamiltonian path. These are also problems that you can use it. Like Hamiltonian cycle is the problem of whether there exists a cycle that goes through all vertices of the graph only one time. This problem is also a famous NP-hard problem. You can get some reduction from this one from satisfiability. So this is also the proof of that comes from satisfiability, hardness of satisfiability, but or I will say three-sat. However, the proof is non-trivial. So if some problem that is more similar to this type of cycle, you may want to use the Hamiltonian cycle or Hamiltonian path. Hamiltonian path is that you want to find a path that goes through all vertices only one time. This is actually different from another problem, Eulerian path. Eulerian path, you want to go through every edge only one time. This problem has a simple polynomial time algorithm. Anyone remembers the algorithm for Eulerian path? So the Eulerian path problem is that you want to find essentially a walk in the graph that goes through each edge exactly one time. Not all graphs have such properties, but if the graph has this property that the degree of every vertex is even, then and the graph is connected, then you can do that actually. There is a simple algorithm for that. The algorithm actually, if you want to implement it, I have implemented it. I think maybe recently I have implemented that one with my son. That's a very important and interesting algorithm that at any time, if you, as long as there is an edge that is not a bridge, you will take that edge. So at any time, at any vertex, if there is one edge that if you remove it, the graph becomes disconnected, you don't take it. You will take it the last time that you can take it. So as long as there is another edge that it's like that, you don't take that one until you are forced to do that. This is such a simple greedy algorithm actually for this problem. However, for Hamiltonian cycle that you want to go through all vertices of the graph only one time, so that is important. So here we want to go through every vertex one time. In the previous problem, we want to go through every edge one time. That is polynomial solvable, but this problem is NP-hard. And yeah, and again, I mean, not every graph has it. The question is whether the graph has it or not, Hamiltonian cycle. And we don't, that's also another important and interesting things about the NP-hardness in general. That for a problem like Eulerian cycle, that you want to go through, let me actually just draw the edges. Yeah, so you see in the so this is like a Hamiltonian cycle. Hamiltonian cycle that goes through every vertex of the graph only one time. And there is no. This is another one. This graph. This is a. This is a Eulerian cycle. This is the Eulerian cycle. So we have Hamiltonian cycle and we have Eulerian cycle. Good. And this problem is NP-hard. This problem is polynomially solvable. So it's NP. And it is interesting. So for this problem, we know that this graph has Eulerian cycle if and only if all degrees are even and the graph is connected. And graph is connected. Good. So we have it. We know that it is polynomial. Is the problem clear for the people at Zoom? Is the Eulerian cycle and Eulerian path, Eulerian cycle and Hamiltonian cycle are clear?
Yes.
Good. So we have this property. This is the important thing. So this is, as I mentioned, this problem Hamiltonian cycle is important to prove some hardness for some NP-hard problems, and the proof is non-trivial from three-sat. It is a bit, more work. However, for Hamiltonian cycle, this problem is NP-hard. Interestingly, there is no such if and only if that we are aware of it. So this is very important. For NP-hard problems, like here for Eulerian cycle, we could give if and only if conditions. For NP-hard problem, this is a somehow unknown rule that generally we cannot give such a kind of clear if and only if, or such kind of characterizations of graphs. Which graphs have Hamiltonian cycle, which don't have? We don't have such a clean characterizations. Why? There is no proof that there should be no such thing as far as we know. And who knows, maybe P is equal to NP and then this is not the reason. But generally, if there is such kind of characterization, we should be able to test it in polynomial time, these characterizations. If it is like a good characterization. So in that sense, means that this problem should be in polynomial, like should be polynomially solvable. So for NP-hard problems, generally we don't have such kind of if and only if things. Yes, we may say that if the, for example, degree of the graph is greater than, I think, like n/2 or something like this, yes, then the graph has a Hamiltonian cycle. But it is not if and only if, it is just one part. Such a statement, we can get it for Eulerian cycle. So that is the important things, because if you want to prove some problem is NP-hard or something like this, you need to make sure that there is no such characterization. If there is such a characterization, that characterization itself might be the reason that we can solve the problem. The same thing for matching. For example, for matching in bipartite graph, for example, we have the Hall's theorem, or even more general than for general graph, we have for the if and only if condition to exist like a perfect matching in a graph. We have the Hall's theorem. I don't want to go through that, but because that problem is polynomially solvable. The problems that they are not, that we don't know whether they are polynomially solvable or not, like they are NP-hard, generally there is no such kind of statements. And this is a one important thing that I want to emphasize. Great. Now, having said that, so yes, there are some other problems like Hamiltonian cycle, other than three partition or three-sat, but these are the most important problems that we are talking about them. And anyhow, this Hamiltonian cycle also comes from the three-sat. Everything also comes from three-sat in some sense. Great. Now, let's go through this one. So I will just go this one a bit faster, because we already talked about some of them. So means satisfiability. We are given n variables, and we are each of these variables can be true and false, and we have a Boolean formula which is and or not, and we want to solve it. That is the satisfiability problem. The circuit sat problem is the one that this formula is expressed as a circuit of gates. And that is important. We will talk about this kind of representation of problems later as well. So here we have x2, x1, x2, and x3. This is like and then this is not, and then this is or. And you can reuse. So for example, here, x3 can be used here or can be used here. Good. We will talk about this circuit sat, especially in the sats. The one that is important, the depth of the sat is important. And the depth of the sat is that, like from here to here, how many nodes you will see. Essentially, if you consider it as some kind of, you can consider this one as a DAG. Generally, there is no cycle. Then you want to see what is the maximum length in it. That's important. And another parameter is the number of, sometimes this is also important, that there are some generalization of that. So for example, if you have an and, you may have and of several nodes. And in this case, the number of nodes, like the number of these gates, that the degree is larger than 2 also becomes important. But we will come back to that later. So there is this formula called CNF formula. Okay, so we have this CNF formula. It is called a conjunctive normal form. That is the actual name of it. What is it? So a formula, this is the one that we are considering. This is the formula is and of clauses. Each clause is or of literals, and literals are either xi or not of xi. We discussed that one, and we call it the CNF formula. This also you can consider it as the bipartite graph. So you can put clauses here, and these are like, for example, C1, C2 to Cm, generally they will consider it. And then we will have it x1, x2, x3 bar. And for example, here, C2 is this one. So it is or of these guys. So C2 is or of x1. This is C2 is x1 or x2 or x3. And we want to have all of these guys are satisfied, because we have and of all these guys. And this kind of bipartite graph also is important when we talk about some special kinds of SAT problem. So this is the general SAT, and as we mentioned, in the general SAT, the number of literals in each clause can be unlimited, or like not unlimited, but it can be like as long as m. Generally, we say m is the number of clauses and n is the number of variables. Good. And each the variable that I mentioned, they can be positive or negative. Negative means essentially negation of those guys. We have the three clause that here, these are just or of three literals. And here in the bipartite graph case, the clause degrees would be 3. So we have the 3 essentially clause, exactly 3 in each clause. And we discussed that why satisfiability and three-sat, like if we get a three-sat, when we have a satisfiability problem, we can actually solve it with a three-satisfiability. We discussed that. Now, okay, so these are the important. Now, so far we discussed these things before, and here we want to go some special case of SAT. So as I mentioned again, and I mentioned it before, in satisfiability problems, we generally would like to, in NP-hardness in general, we would like to get problems which are as specific as possible. For the lower bounds, we want to do that. So we not only we talk about the SAT, it is NP-hard, we talk about three-sat. Not only about three-sat, but also this one. Three-sat 5. What is the three-sat 5? Each variable occurs in at most 5 clauses. So we, in some sense, if you consider this bipartite graph, we already mentioned that the degree of this guy is 3, the clauses. Here we want to say that the degree of each of these variables also, I mean, this is actually including both the variable itself and this negation. That degree is also at most 5. So even that case is the problem. This is the case that the problem is hard. And this is this paper of, I mean, Feige, JCM, and probably earlier than that. Good. Now, note that consider this bipartite graph. In this bipartite graph, we have positive and negative. It's a bit annoying that you have a variable x1 here, and then you have another variable x1 bar here. Because then these two are somehow related, and we talk about the degree, these are the degree of the both of them. So here the idea is that can we also remove that, make a nicer things that we can use it for other graph problems. So we try to get as specific as possible, and we want to exactly understand which problems are easy, which problems are not. Good. Now, okay. So this is the version which is called monotone three-sat. What is the monotone three-sat? Each clause, in each clause, all guys are positive or all negative. So if you consider each clause, either each clause is somehow like x1 or of x2, x3, or something like this, I don't know, x6 bar, x7 bar, and x8. So all of them, this is called the monotone. All clauses are in this form, either of these forms. And note that this is also important. This is one reduction which is important. If you here, we consider like a new problem, that in this problem, each variable is just a negation of the current variable. So define something like this. Y1 is equal to x1 bar, and so on and so forth. So if you do this reduction, that if so essentially x1 will be, then x1 would be y1 bar. Good. So we can have this reduction that x1 goes to y1 bar and x1 bar goes to y1. If we do that, this is a reduction that sometime we will use it. I will talk about it. But if you do such a reduction, still this formula remains in the same form, because again, because this is monotone. So all of them, all these guys becomes now negation or not, and all these guys become positive. So we can do this type of reduction that we go from one variable to the negation of that. We can do that, and that sometimes is helpful. Any questions so far? Is everything clear? Good. So let me clear everything and then go to the next one. Good. So here we want to see which version. So we mentioned, okay, this is three-sat. Then three-sat 5 means that the degree of each variable is at most 5. It is still NP-hard. Not only that, also if we are assuming that each clause, either all positive or all negative, still is NP-hard. Now the question is that in which cases the problem becomes actually easy, means polynomial is solvable, because we should be careful about it. So, of course, the most famous one is this two-sat problems. What is the two-sat problem? We have just or of two literals in each of these cases. With how many of you have written algorithm that solves two-sat actually? Have you done that? Yeah. So that's actually interesting. So this two-sat, if you don't do it correctly, this is one of the things that actually writing is some kind of greedy algorithm that works. But it is a nice way of solving the problem. This way that actually becomes very natural. How can we solve it? This is actually easy to see. So we have like each clause is just x or of x and y. Good. Now, instead of that, we can write this one in this formula. So this is essentially this results in. So here essentially saying not x results in y. So for this operation, so what is this operation? This operation is this one. So the Boolean formula, we have and, or, not, and this resulting. Is there any better name for that? Concludes essentially, or you have implies. Yeah, implies is better. That also used. There are several names for it, but yeah, implies actually might be better. So implies, when you use imply here. So what is the implies things? Implies is actually simple. It says that when you have P implies Q, if here, if P is false, independent of Q, the whole thing is true. So it means that if you say based on some nonsense, if you condition on some nonsense, then everything else that you will say is true because based on nonsense. However, if P is true, then in this case, the result would be exactly equal to Q. So if Q is true, then it is true, and if Q is false, then it is false. Now, it is easy to see that X or Y, it is equivalent of this. Not X implies Y. Good. Now, or you can equivalently say this one, not Y implies X. Now, then you write this one. So essentially all of this formula that are in this form, that X1 implies Y, I don't know, maybe not of X1, it implies Z, and then Y implies W bar, and then W implies, say for example, T. Maybe I should use Q, and so on and so forth. So we have, so the whole formula, the three-sat formula would be something like this. So essentially these are and of these guys, correct? These are and of all these guys. Good. So all of the things would be like this. Then how do you solve it? If you write this one, actually, it would be easier to actually write the algorithm, or at least the implementation would be cleaner. So first you are replacing everything with this one. Now what do you do? Then you will start from one variable, x1, and then you will put that one true. Now, if this guy is true, because everything should be true, like we want to have essential satisfiability of everything, it means that if x1 is true, then here y should be true as well. Here actually I use x1 instead of x, but anyhow. So yeah, so if this guy is true, then this guy should be true. Good. Now, if this guy is true, then this guy should be true as well. So if this is true, it means that W bar should be true. So this should be true as well. So we just see what are the set of implications that we have. Now, here x1, if x1 is true, then x1 bar is false, correct? In this case, you can just remove this guy from further consideration, because you know that that is always true. So that's a very nice way of implementing this one. So you will start from this guy and you will continue. And here, of course, I mean, if it is, for example, here, and then we have, maybe you have such a thing, like W bar implies X bar. So because W bar was true, then here, this means that X bar also should be true. This is a contradiction. Good. So anytime that you are, so you are starting from one variable and you will continue greedily the set of implications. If you reach a contradiction, you will come back and you will change that variable. So we put x1 equal to essentially true here. However, we could put x1 equal to false here as well. So then we can try with false. Whether with false, what will happen? If both of them fail, then this problem is not satisfied. Otherwise, so if one of them fails, that is the interesting thing. If one of them does not fail, it essentially makes some of the assignment, it makes some clauses, makes lots of clauses true, and then we can remove them for further considerations. Then we are remaining with a reduced instance, and then we need to solve the problem for that one. Again, in that reduced instance, we are guessing one variable and you will continue. And if you reach a conclusion, you will just change that greedy choice to false, like from true, you will do it to false, and then you will get the things. If none of them works, it means that the formula is not. And it is important. The greedy algorithm is this one, that you start from this, you will get some things. And if it does not work, you will change it. But if it does not work, then, I mean, you just, both of them does not work, the formula is not satisfiable. However, if one of them works, then you will delete everything and then you will just remain with a reduced instance. You don't need to consider the false case in that case. So you will try the false case, only the true case does not work. And then this is the greedy algorithm that works. So this is a simple algorithm that, especially with implications, is much easier to see that why is it the case. Because whenever this guy becomes false, then you can remove this one because that is irrelevant. And of course, if this is true, then, I mean, this guy is true, then it has some implications that you are making all of them true as. Is the algorithm clear for two-sat? Okay, so this problem, as I mentioned, two-sat is satisfiable. However, another problem which is called max two-sat. This problem actually is NP-hard. What is the problem? Is that you want to set the variables to maximize the number of true clauses. So you have essentially the input is exactly the set of the three-sat input. However, the catch is that you don't, possibly you cannot satisfy. So if you run, of course, you can run two-sat, see whether you can satisfy everything or not. But say you cannot satisfy everything. Now the question is that, okay, you cannot satisfy everything, but satisfy the maximum number of clauses. In this case, even max two-sat problem becomes NP-complete. Now, interestingly, what would be the, so the question is that, can you get, if a max two-sat is given to you, what would be an approximation algorithm that you can get it essentially for the problem? So do you have any ideas how you can, I mean, give some algorithm for max two-sat. So somebody is given to you. You know that, I mean, you cannot satisfy everything. The question is that, can you do anything? I mean, maybe you cannot get a, like when the problem becomes NP-hard, we may not be able to solve the problem exactly. So we try to get some approximation. And what would be a good approximation for max two-sats?
Trying to set sets of clauses in order to satisfy two-sat kind of add clauses.
But can you say that that is a good algorithm? Yeah, so that's actually a very simple algorithm. Each variable, so this is this kind of randomized algorithm. Put each variable true with probability half. So this is the randomized algorithm. Each variable, you will set it equal to true with probability half. Then how many clauses you can satisfy? What is that?
2 power.
Let's say it's two sat even. Yeah, I mean each clause there is a 3/4 that it becomes true. It becomes false only if both of them are essentially put false. So this algorithm actually satisfies 3/4 M clauses. So always actually we can satisfy. So this is randomized, but you can de-randomize it. It is called a conditional expectation approach. That the algorithm is also, I mean, simple. I mean, you will decide whether one variable you will put it true or false based on the what would be the expectation of the remaining clauses. How many we will essentially satisfied if you put it true or false. If you put it this way of greedy algorithm, actually you can get this algorithm 3/4 approximation. Now, for this problem, there is a 3/4, and if I not mistaken, actually you can improve a little bit over 3/4. But when the problem becomes max 3 sats, that max 3 sat, actually the best things, again, the same thing. For max 3 sat, if you do this randomized algorithm, what would be the result? How many you are satisfying? 7, 8. For max 3 sat, this is, I think this is part of the PCP theorem, that this is the best approximation that you can actually get. For, I think for max 2 sat, you can improve it a little bit over 3/4, but not for 3 sat, as far as I remember. Yes, so, and this is very important. So this one that you cannot do anything other than this trivial algorithm is actually, that's the whole idea of the PCP theorem that we will talk about it, probabilistic checkable proofs. That we will talk about it later for the approximation algorithm. And note that here, the upper bound that we are, why this is a 3/4 approximation? Because whenever we talk about approximation algorithm, we need to talk with the optimum algorithm. What is the optimum here? Yeah. So in this case, the best case is that you can satisfy everything. So we are using trivial upper bound of M here. And this is also, again, as I mentioned, this class in some sense is a class on hardness, but we talk about algorithms as well, like the basic algorithms. Then we talk about the hardness. In some sense, is the advanced algorithm class as well. So here, for any problem, for this approximation algorithm, like generally for NP-hard problem, one way to attack them is getting like not an exact solution, but maybe we can get approximate solution. When we talk about approximation, because of these other things that I have mentioned, generally for optimum solution, there is no if and only if. So we don't know what is exactly optimum, but we try to take some imaginary optimum and try to massage it such that we can get some bound on the optimum. That's a typical things that we are using a lot in approximation algorithm in particular, or actually the other areas. So this is the optimum. As I mentioned, for NP-hard problem, we generally don't expect that you have if and only if, nice characterization of optimum. So this is some imaginary optimum. We may just do that. Okay, if optimum has this shape, can we massage it and make it this nicer form? So we make nicer and nicer forms such that we can now compare ourselves with that. During this massage, you may lose a little bit in optimum. So for example, here, I mean, we are just using the trivial bound. I mean, we don't know what is optimum. This is a trivial bound. We said, okay, at most would be M. If I can compare myself with the number of clauses, which is M, then I have approximation algorithm. I don't know what is optimum. It might be the case that it is 3/4 that I will get it, or 7/8. Actually, that's the optimum. And I get one approximation for the problem. But I don't know. I will say in the worst case would be M. And yeah, so this is the type of things that we are working when we try to design algorithm for NP-hard problems. There is no good understanding of optimum. We need to massage the optimum such that we have a better understanding of optimum. And during these operations, we may lose, some approximation factor. You will see this more and more in this class. Does it make sense? But that is the general idea of the designing algorithms or attacking NP-hard problems, that we don't have a good understanding of the optimum. That's the reason that we need to massage it and maybe lose something in approximation. Great. Okay, so this is the algorithm that I mentioned for max sat or max 3-sat. Now let's. And I mean, generally, it would be good if you come on time, or you can, if there is some, yeah. Like, I mean, I'm not just talking to you, but the others, they were like, I mean, if there's some time, sometime late, you can actually do it with Zoom as well, because we have Zoom as well. Or I mean, if you want, actually, this is another thing. You can have, if you come, for example, with a bus and the bus is late, you can actually use your cell phone. You can connect with a cell phone to Zoom, and you can just, as long as you have some headphones, actually, you can connect to the class so that you don't miss it. Because the issue that I mentioned, it is like, I'm teaching the class and it is available. But the issue that I don't want that your time is wasted, because if you come and you didn't maybe hear the first part of it, maybe the second part does not make that much sense. So as long as you have some kind of starting from that, you can come through Zoom and then change it, like with the cell phone, and then change it to this. Even you walk, you can listen actually. Great. Okay, so we talk about the max 2-sat. Now let's define this other one, the horn sat. The horn sat is actually the generalization of 2-sat. So here in the horn sat, each clause has at most one positive literal. So this is a satisfiability problem. We discuss essentially the clauses, and this clause has several literals. Here, it says that each clause has at most one positive literal. So for example, this is an example. So we have not of x, so this is one clause, not of x or not of y or not of z or w. Good. Whenever we have such a things, actually we can represent that one with this formula. So we can say not of, this is the Morgan's theorem essentially, that not of x and y and z, it becomes to not of x or not of y or not of. So we just get this one. And then what do we get out of it? Then we can represent that one as the implications, that the one that we have like implies. So we can say x and y and z implies w, because that formula that we discussed here. So we mentioned that if this formula is equivalent of, so we can essentially change the OR case. So we have here OR of w and this formula. So when we have OR of this formula and this formula, we can actually change it and we can write it in terms of implications. So here, instead of this formula, we can write it this. Then it is, then you can actually we can solve as long, because we can change into this form, then actually we can easily solve these problems via a 2-sat essentially. And again, I think this is the one that I have mentioned here as well. So whenever you have this formula, I mean, you can just also, yeah. So you have this formula, you have this kind of implications, and whenever you have the implications, you can solve it using the two-set algorithm. That you will guess one variable greedily. If it works, then it works. Then you will delete all these clauses. If it does not work, then what you do? Then you will go and change that variable, and you will. And again, note that, I mean, this is not actually important whether W is here or here, because you can always also, these formulas, you can change it. So X, or you can write it not of X or Y, or you can write not of Y and X. So which one is here is not that important. You can bring any of them in the first part. Now, there is another one, which is good. So, and again, this is the one that I have mentioned. So I mentioned that so this is another one called dual horn. What is the dual horn? Is a dual of that one. Each clause has at most one negative literal. So it is, I mean, Schaeffer's, I mean, 1978, it called it the weakly positive satisfiability. So each clause has at most one negative literal. Why this problem is the same as the horn sat? Yeah, so we can just rename the variables, as I mentioned before, that X can go to Y, X1 can go to Y1 bar, and vice versa. So if you do that, actually, then there is no changes. You have done it, and this problem and the horn sat would be the same. So this problem is also polynomial solved, and this is the one that I mentioned. So if you have PQ, you can actually replace PQ with not of Q and not of P, implies not of P. Now, so this one, we talk about the satisfiability problem, or CNF, conjunctive normal form. What about disjunctive normal form? It is called DNF. So this is the reverse of that. We had in the CNF, we had and of ors. Here we have or of ands. And that's actually, this one is easy, because this formula is satisfiable if there are at least, as long as there is one clause and there is no contradiction in the clause, then we are fine, because we have or of ands. So it means that like you can just focus on one clause. And in that one clause, as long as we don't have a contradiction, like if we have X1, because this clause is and of these guys now. So we cannot have Xi and Xi bar, because one of them, that is a contradiction. So if we have such a thing, we cannot satisfy that clause. So we need to focus on other clauses. But as long as we have one clause that does not have any contradictory things, it is and of something. Just put all of them true, and then we are good. Good. So more versions of SAT actually, and these are important. I will mention that, especially the few important ones that will be very useful to get results for proving the problem are that some problems are NP-hardness. So what is these things? Good. So what are the other versions? So the other one, this is the one that is interesting. 1 in 3 sat. What is 1 in 3 sat? Or it is sometimes called exactly 1 3 sat. In lots of them actually belong to Schaeffer, that we will talk about it. So in this case, each clause has exactly one of these three literals should be true. So in the three set, we say that okay, at least one literal should be true. But here we say that exactly one should be true. So for example, if there are two, these are the false. So this is the only true ones: TFF, FTF, and FFT. Anything else would be false. So even if you have two true, still it is not, you have not satisfied. There is another version called like monotone 1 in 3 set. Here, we don't have any negations. All literals are positive. Good. So this is essentially, we had exactly 1 in 3 set that one of them should be true. Here, because of course, if we don't have this assumption that 1 in 3 set, then if you put all positive, then you put, then put everything true and then you will satisfy. However, it says that monotone 1 in 3 set. It means that there is no negations. All of them are positive. But in each clause, only one of them should be true. Why this is important? Because of this bipartite graph view that I have mentioned. So I mentioned that you can put essentially clauses at the top and the variables at the bottom, the V1, V2, V3, and so on. Here, because of this issue that there is no negation, then you can actually, this C1 only has some variables. Everything is positive. So we don't have this issue of, for example, we don't have this issue of that V1 bar variables because this does not appear. If you have it, so the question that, okay, sometimes I'm connecting to this, sometimes connecting to this, what is the degree of this vertex? And these guys are somehow correlated because one is the negative of the other. But here, I don't care about it because all clauses are positive variables. So this one here, and this problem is also this problem also is NP-hard. However, there is another one which is called monotone, not exactly 1 in 3 sets. So what's the meaning of non-exactly? So this is important. If you have monotone 1 in 3 sets, in each 3 set, you want to satisfy only one of them. And all of these variables are positive. All the literals are positive. I don't have any negation. Still, this problem is NP complete. However, if I say monotone not exactly in 3 sets, what is the monotone not exactly? That each clause you need to have satisfied either 0 or 2 or 3 variables. So it is exactly the reverse of this guys. Then in this case, actually, this problem is polynomially solvable. We say we will go there, and for 3 sets, we want to get the very specific cases, which one are polynomially solvable, which one not. If you say 1 in 3 should be true, it is correct. But if we say that not exactly 1, like not 1 in 3 sets, it means that either you can have 3 false satisfied, or 2 false, or 0 true, or 2 true, or 3 true. These are all the satisfiable things. In this case, actually, this problem becomes dual horn. So that dual horn is important. Why? Because you have 3 variables. You have xi, xj, and xk. So you can write it actually. So if we have this one, for example, we have write it x1, x2, x3. Here I'm assuming all of them are positive. There is no difference. So I can write it like this one. So I will write it x1 implies x2 or of x3. Then I can write x2 implies x1, x3. And then finally, x3 implies x2 or of x1. Correct. x1, x2, 3, x2, 1, 3, x3, x1, 2. Good. So here you can see that. So for this, I will write it like this. Good. It is easy to see that if only one of these guys is true, then this statement is these three of them. I will put, of course, and of all of this. This is and of. Good. If all of this, if only one variable here is true, then you cannot satisfy that. In all other cases, you can satisfy them. Why? Because if one of them is true, say x2 is true, and you know that these other guys, both of them are false. So this would be true implies false, which is actually implies essentially the value of that would be false. So you cannot satisfy this one. So if this guy is true, this other guy should be true as well. So this 0, 2, and 3, you can write it like this. And this would be dual horn. I mean, essentially the one that you can actually write it in terms of implications. So and you can just use it that greedy algorithm that we mentioned for dual horn or horn divergentization of the two sets. So this instance is polynomial solvable. There is another one which is also interesting. So this not all equal 3-sat. What is not all equal 3-sat is that not all, so this means that these three literals, not all of them should have the same value. Of course, in the 3-sat, we said that they should not all be equal to false. Here, I will say that all not like all equal to true is also not desired. You are satisfying a clause if not all of them are equal. So, as I mentioned, so the forbidden case are these two. Everything else is possible. And you know, these are the things that the people consider from SAT, they went to 3-sat, they consider very special cases. Because these special cases, if you prove them actually, then the life would be easier to prove some other problem. For example, this problem that I have mentioned, this monotone one in 3-sat. Here we don't have any negation variables. So that's actually a very nice bipartite representation of the SAT. We are using this to prove something for graphs, essentially, that are hard. And you can even consider the planar version of that. This graph that you are doing it here, this bipartite graph should be planar. You should be able to draw it in the plane such that no two edges are intersecting. We can show that even that actually is hard. And that we use it to show that some problems or on planar graphs are hard. Planar graphs are the graph that you can draw the graph essentially on the page, such that no two edges are intersecting. So to prove that such, and this is the road network, for example, lots of networks actually are almost planar, the practical things. So to show that for this particular planar graph, which is a very natural practical application, whether the problem is hard or not, you need to use SAT, you need to change it from 3-sat to this monotone one in 3-sat, then you need to consider the bipart, then you have a nice bipartite representation. If you have V1 and V2, this graph is not a very nice bipartite representation because we have both V1 and V1 bar or negate of V bar. But we will, because this monotone is hard, then we don't have such a things. And then this graph is a bipartite graph. Now you consider the planar version of that, and then you say that even the planar graph is hard. Good. So that's the way that you need to go and show for very specific things, such that we can say that this particular problem on this practical graph, actually, I don't have any solution for as well. Like it is, at least so far. Any question so far? So the people on Zoom, do you hear me? Well,
yes.
Good. Yeah. I think Ali has replaced. Previous time Ali was there. I was asking him. Now this time others are there. Good. So of course you can. So this is the one. We have also this one, the monotone, not all equal three-sat. So lots of them actually belong to Schaeffer. I mean, he has considered actually lots of this. So Schaeffer in 1978, lots of these versions actually he defined it in his seminal work. Actually, he didn't mention this version, but this version also is NP-hard. Monotone, not all equal three-sat. There is no negations, and all these roles are positive. Again, this is very important for the bipartite representation. This problem is also NP-hard. Good. Now, which problems are the most practical one? These two problems especially. So these are the ones that, so this monotone, not all equal three-sat is also NP-hard. Then the one that you actually want to remember is this one, the three-sat itself. That's a very good problem to use to show some problems are hard. 1 in 3 sats, that is also is a nice problem to deal with. And last but not least, not all equal 3-sat, or even the monotone not all equal to 3-sat. These are the 3 problems that these are the most useful ones. That if you use it, that makes the life much easier. We will see some examples of this. Or this variance of the problem. Is it clear? Good. Okay, so this is Schaeffer's. I mean, he has actually defined several variants of these problems, as we discussed. Now, he has this kind of Schaeffer's dichotomy theorem or universal theorem that he proved actually in stock 1978. So that's essentially the idea. So he considered all these variants. And then he wants to say that which of these variants are polynomial solvable, which of them are not polynomial solvable. So he says this one. So this is essentially the theorem. You can read the exact statement there, but this is somehow the things that we are considering. So what is so a formula is the end of clauses. Good. So assume that a formula is the end of clauses. And a general clause is some relations on variables. So we have end of subclauses, and each clause is some relation on the variables, not necessarily or. It can be, I mean, essentially even more complicated than that. And so, I mean, actually here he's mentioning that should be also in the CNF formulas. Good. So if you have such a general theorem, so you have a general representation of satisfiability problem. This is the thing that he mentions. He said that this satisfiability problem is polynomially solvable if either of these cases happens. What are these cases? So the cases in some sense that we have seen it so far. He said that one case is that so it should be one of these cases that this general satisfiability problem actually is solvable. Either if you set all variables true or all variables false, satisfy all relations. That's one case. But you put it all of them, you should try all of them true or all of them false. If it satisfies, then we are. Or these subclauses, as we mentioned, essentially these are like each clause is a relation on variables, and this is end of some subclauses. Or when the subclauses are all Horn or all dual. As we mentioned, Horn and dual Horn, these are the easy cases. Or all of these relations are 2 CNF. So essentially, he said that these guys have only two instances. Like this is max. Essentially, it's a two-sat. So in some sense, this is intuitively either you should put all variables true or false, and then it works, or it should be all of these clauses, sub-clauses should be horn or dual horn, or all of them should be like have two. Essentially, all of them should be like two sats. The last but not least one, this is the interesting thing. Or every relation can be expressed as a system of linear equations over Z2. This is the one that we didn't consider. We will talk about it. He said that if these are not these cases, then this sat instance is NP-hard or NP-complete. So in some sense, the easy cases of sat are this case. Either all of them are true, put it all of true, or all of them false. And again, this formula is a little bit more than CNF. So it is talking about sub-clauses, and each of them can be essentially, each clause, you have some sub-clauses. You can see the exact theorem. But anyhow, he said that either it should be trivial that you put all variables true or false, it is satisfied, or all of them should be horn or dual horn. Horn and dual horn, what was that? In the horn is that all of them are positive except one which is negative, or vice versa, that all of them are negative and one of them is positive. Or all of them essentially are the two sat instance. Otherwise, the sat is NP-complete. The only remaining case is this one, this one. So let's discuss this case. This is actually important. So this is a case that also we can solve the problem in polynomial time. What is this case? It says that each of these relations, so we had essentially and of some clauses. So we had and of some clauses. That's the thing that we call it. So that's the thing that I mentioned. This is in the CNF. So when we have this and of clauses, each clause, the formula is equivalent of this. So we have it, for example, xi, x or xj, x or xk, x or xl is equal to 0 or false. So we will consider this one over Z2. Z2 means 0, 1. And of course, I mean, XOR, you know what is XOR. XOR of xi, xj. When is the case that XOR is true and when is the case that it is false? Yes. So if one of them is true, then it is true. Otherwise, it would be false. So in some sense, that is the reverse of this not all equal case, essentially. Not all equal. Actually, this is exactly the not equal case. So it means that if they are both of them are true or both of them are false, then it is false. Otherwise, it is true. Good. So, and you can like generalize this one to more things. You can have more than two variables. So if you can write, so you have and of some clauses, and each of these clauses you can write it as a system of this linear equation. This is the linear equation. So this is somehow, so we have the linear inequalities, like this is one that we can solve it using Gaussian elimination. This is the same version essentially on Z2, but we write it with XOR. So instead of plus in the linear formulas, we have XOR. So we say that if we have XOR of these guys, there should be 0 and 1, and the system of this equation. If each clause has such a property, then using the Gaussian elimination, we can also solve the satisfiability problem. So these people actually, they consider this problem of, CNF. The people are still using, doing it for constraint satisfaction problems. If you read them, so all of them is like has a similar flavor. The case that we can solve it is the case that we can write this equation in terms of this system of equations with XORs. If we can do that, these problems also we can solve it using Gaussian elimination polynomial. And this is the Schaffer's universal theorem that we discussed. So he tried to essentially satisfy the very general formula when the problem is NP-hard, when it is not NP-hard. And he could prove that. Good. So next time we are giving some examples essentially from these things. We are especially giving two examples. I mean, one is easier, the other one is harder. And these are, I mean, some games, some graph problems that we show that these problems are actually NP-hard or NP-complete. And we show that if we are using three-sat, the problem might be a bit harder to prove. But if we are using like some variations that we have mentioned, as I mentioned, these two variations are very important. So sometimes if you want to just use it three-sat, it might be hard to prove. But if you use it one in three-sat, or not all equal three-sat, or actually monotone not all equal three-sat, then the problem becomes much easier to prove. And we will see some examples of that next time. Great. So any questions? Yes.
In this Hughes theorem or whatever, what case covers like just one clause and three things, and the rest fault?
Sorry, one clause of what?
Three.
Yes. For example, that can be the case of like this, the last inequality. The last one. So the question is that, I mean, if we have one of these variables has only, for example, this case, this would be the cases, for example, this one. This is the case that if you have one variable, essentially one clause has three variables, all of them have one, for example, something like this. Then this can be a special case of this, or it can be a special case of Horn and double. So you can read the exact theorem, at least the exact thing. So I just gave the intuition, but you can actually read this. I think it is also in the book, a more complete version of this. Also, you can see it in the paper itself. So what does it have? But this is, I try to give the general ideas to you. Any other question from the people who are on Zoom? Great. So if there is no other question, I think we can finish the session and then we will meet Thursday. Let me stop share. Okay, so have a good day.